This is the second video about section 1.6, the very important topic of a phase line. It's very important especially because it helps preview the main topic of chapters 2 and beyond, which is phase planes and all sorts of systems of differential equations where we can make phase planes. Let me review the idea of a phase line by doing another example. We'll take an example from a book. I'm purposely picking kind of a strange example. It happens to be number 12 from section 1.6. One reason it's strange is we're going to go ahead and use a different letter for the dependent variable, w instead of y. The w dt is going to be the left-hand side, so that's one strange thing here, is we're going to use a w instead of y. You know, the use of y is not set in stone. You are certainly free to use whatever letters you feel like you want to use for a differential equation. In number 12, dw dt equals w squared minus 1, that entire quantity, times the arctangent of w. The arctangent of w is the same as the inverse tangent of w. And I'd like to try to draw the phase line for this and find sinks, sources, and nodes without relying on a computer. So we'll try to rely on the knowledge that we have about functions to see if we can come up with the phase line for this. This is certainly a good skill to have. On an exam, you really do want to know these things so you're not too bogged down in trying to get your calculator to do it. So let's see if we can figure that out. First thing we can do is this left factor in the right-hand side is pretty easy to factor. That's just w minus 1 times w plus 1. So we can think of this function in this way on the right-hand side. Since we're already using different letters for the dependent variable here, I'll go ahead and use a different letter for the function name. Instead of calling it f, I'll call it g. So I'll think of the right-hand side there as being g of w. So I definitely have roots to the right-hand side at w equals 1, w equals negative 1. Any others? Well, it depends on what that arctangent function is doing. What is the arctangent function? Can you try to remember that without a calculator? Let's see if we can recall what the arctangent function looks like without relying on technology. So this is a little side calculation, or a side picture. First of all, let's see if we can remember what the tangent function looks like. To do that, we need to remember that tangent is sine divided by cosine. Let me just lightly draw in a sine and cosine curve in here. Here's the sine curve. Oh, this is such good practice, such good review. So that dashed curve is the sine curve. Here's the cosine curve. Let's see, it looks about like this. Keep those straight in your mind. The first one I drew was the sine, going through the origin. The second one I drew was the cosine, going through the point 0,1. Tangent of x, or tangent of y, or tangent of w, I guess in this case, is the sine of w divided by the cosine of w. So I need this curve divided by this one. That's going to be 0 wherever the sine is 0. So tangent has the same zeros as the sine function does. And it's going to have vertical asymptotes wherever the cosine function is 0. So, for example, the tangent function has vertical asymptotes at negative pi over 2 and positive pi over 2. It's 0 when w equals 0. And it's positive over here, negative down there. That's what the tangent function looks like between negative pi over 2 and positive pi over 2. Turns out this function repeats. It's a periodic function with period pi. The graph continues to have the same kind of pattern to it forever and ever in both directions. That pattern would continue. As far as the arctangent function, though, goes, all we really care about is this first piece. See, the entire tangent function is not invertible. It doesn't pass the horizontal line test. Many horizontal lines, in fact, all horizontal lines, go through it more than once. In fact, infinitely often. It's definitely not a one-to-one function, so it definitely doesn't have an inverse. However, if we restrict the domain, if we only consider the piece where x or w goes between negative pi over 2 and positive pi over 2, that one piece is one-to-one. We can ignore the rest. That one piece does have an inverse function, and the inverse function, the graph at least, would be the reflection of that graph across the line of slope 1 through the origin. So the graph of the inverse tangent function, it's a bit hard to see here. If you imagine trying to reflect the graph of that main part of the tangent function across this slanted line, you get the one that I'm really trying to make boldface here now. Again, you ignore that one, you ignore this one, just focus on this one and the dashed line that's slanted. Turn your head at a 45-degree angle and you can see that the reflection of that is the one that I made in bold. That's the graph of g of w. It has one root at w equals 0. Okay, so we went through all that work trying to avoid a calculator to remind ourselves that this has one root at w equals 0. It's positive when w is positive and negative when w is negative. I guess, excuse me, I labeled this badly. That's not g of w, this is arctangent of w. Let's try to predict what g of w looks like by thinking about where this is positive and negative there. So now we're going to go ahead and try to graph g of w. It's got roots at -1, 0, and 1. And it will be a continuous function. W minus 1 times w plus 1 is a polynomial. It's continuous. And the arctangent function is continuous for all values of w. This definitely will be a continuous function. If we can figure out the signs of this function, positive or negative, in between these roots, that will definitely help us draw the graph if we try to avoid technology. Let's think about w between 0 and 1. When w is between 0 and 1, go up here, the arctangent of w is positive, w plus 1 is positive, but w minus 1 is going to be negative. So the graph of g of w has to be negative in between 0 and 1. I'm not sure how far down it goes, but this is all qualitative anyway, so I'm just going to emphasize that it's negative. When w is bigger than 1, all three of these factors up here are positive, and so the graph becomes positive. It goes above the w-axis. And in fact, because the quadratic part goes to infinity as w goes to infinity, the graph of this would continue going up, even though the arctangent of w approaches a limit as w goes to infinity. When w is between -1 and 0, arctangent of w is negative. W plus 1 will be positive. W minus 1 will be negative. Negative times positive times negative is positive. The product is positive. So our graph is positive over there. And finally, when w is less than -1, all three of these factors are negative, so the product is negative. So we get something that looks like a cubic. So what does the phase line look like? Thinking back to what we learned in the last video, we draw a vertical line. This time I'll label it with W. The places where this right-hand side is 0 correspond to equilibrium solutions for the differential equation, which for the phase line correspond to equilibrium points. So you want to make sure you mark those points, 1, 0, and -1. Those are stationary with respect to this phase line. You might think of this phase line as having a flow to it, that points move according to the arrows that I draw, but these equilibrium points stay where they are. They don't move. What about the arrows in between? Coming back over here when W is positive, G of W is positive, so going back to the differential equation, dWt is positive, dW dt is positive. Solution curves increase, so on the phase line, I draw an upward pointing arrow. When W is between 0 and 1, G of W is negative. Going back to the differential equation, that means dWt is negative for W values between 0 and 1. So solution curves are decreasing. Coming back down to the phase line, that means I draw a downward pointing arrow like that. When your W is between 0 and -1, G of W is positive, therefore dW dt is positive. Solution curves are increasing, therefore I draw an upward pointing arrow. And finally, when W is less than -1, and that's -1 there, G of W is negative, so dW dt is negative. Solution curves are decreasing, and therefore on the phase line you get a downward pointing arrow. So we've got 3 equilibrium points. The phase line looks like this. This one is clearly a source at 1. 0 is a sink. Nearby points go towards 0 as time goes on. Nearby points to 1 go away from 1 as time goes on. And -1 is a source. Source, sink, source. We've got no nodes in this case. So that's a brief review of phase line. In the rest of this video, I want to focus on more abstract ideas, and in particular something called the Linearization Theorem, that will allow us to use the derivative of the right-hand side to identify when we have sinks and sources. Try to motivate it by looking at this picture. This is the right-hand side. It's G of W in this video. Kind of looks like a cubic. It's technically not, but it has that kind of shape. Its derivative, I suppose, will kind of look like a quadratic. The derivative of the right-hand side, G prime of W, would look like a quadratic. In particular, it's going to be positive when W is to the left of that vertical line, negative when you're between these two vertical lines, and then positive when you are to the right of the vertical line on the right. And in particular, thinking about the slopes at these equilibrium points for the differential equation for the phase line, the slope here is positive, the slope here is negative, and the slope here is positive. Now, the fact that those slopes are positive, because the derivative is positive or negative, depending on which one you're at, and the fact, well, that's enough to tell you that the graph of G of W crosses the W axis. It doesn't just touch it, it crosses, okay? If you look at the last video, I did a couple examples where there were graphs that just barely touched the horizontal axis. They maybe came up to it before going back down, or came down to it before going back up. So you had roots of the right-hand side at those values of W, but the graph didn't actually cross it. And if you look back in that last video, that kind of behavior led to nodes. The fact that these derivatives are non-zero at these equilibrium points means we're not going to get a node, because it means the graph of the right-hand side changes sign as W passes through those points that are going to be equilibrium points. That's going to happen in general if you've got an equilibrium point for a differential equation, so let's try to outline the theorem here that I'm getting at, this linearization theorem. Linearization is what that's supposed to say. Theorem. I'm not going to state it precisely here at first. In fact, I'll leave that to you looking in the book. Well, let's try to get the gist of the idea. We've got a differential equation. I'll go back to dy dt and f of y. It's autonomous, okay? Well, we're dealing with an autonomous equation. The right-hand side only depends on y. Let's assume that we've got an equilibrium point. Assume y equals y sub 0, or maybe I'd just say y sub 0, is an equilibrium point. Equivalently, y equals y sub 0 as a constant function would be an equilibrium solution. So y0 is a root of the function on the right-hand side. We want to know, on the phase line, is y0 a sink, source, or perhaps a node? The idea here with the linearization theorem is to use the derivative of the right-hand side to help us decide. If the derivative at this equilibrium point y0 is positive, based on this example, we might hypothesize that that equilibrium point is going to be a source. Why? Well, because this -1 and the positive 1 were sources, and they corresponded to places where the right-hand side had a positive derivative. And they were sources over here. Thinking about the sign of the right-hand side, because those slopes are positive, the sign of the right-hand side changes from negative to positive as w passes through those points. Negative to positive. So that's what's going to cause you to get sources. Solution curves go away from those equilibrium solutions through those points as time increases because of the sign of the right-hand side. Positive when you're above this one, negative when you're right below it. On the other hand, if the derivative of the right-hand side is negative when we pass through an equilibrium point, slope here is negative, the graph of the right-hand side changes from positive to negative. 0 was a sink for that equation, and in fact, it will be in general for this theorem. If you've got a negative derivative at an equilibrium point, you'll get a sink at that equilibrium point. There is an extra hypothesis that we need to have to truly make this theorem right, to make it a definite theorem. We need to assume our function g is extra nice. All right? The technical assumption is phrased like this. We assume, oh well, I guess down here is the function f. Assume f is what's called continuously differentiable. You probably have never heard that phrase before. You've heard of continuous and differentiable by themselves before. Continuous meaning it's got no breaks in its graph, and differentiable meaning its graph is smooth, the derivative exists everywhere. Continuously differentiable means a little bit more. Not only is it differentiable in that the derivative exists, but it's also, that derivative is also continuous. So f prime exists, and f prime is also continuous. Now the fact that f prime exists, so that f is differentiable, is actually enough to mean that f itself is continuous and has no breaks. But just because the derivative exists doesn't mean the derivative is continuous, which is kind of hard to imagine. I'm going to show you an example in a few minutes of that. Just because a derivative exists doesn't mean the derivative is continuous. Very strange sounding thing. It does mean the original function is continuous, but not necessarily the derivative itself. So we need this extra assumption basically to guarantee that nothing real strange happens. Because if you just assume f is differentiable, strange things actually can happen. like the derivative exists, but it's not continuous. And trying to summarize this theorem again, basically it says if the derivative of the right-hand side at the equilibrium point is positive, it implies that the equilibrium point is a source. Okay, technically speaking, the right-hand side needs to be defined and continuous and differentiable, and continuously differentiable near the equilibrium point, at least on some open interval around the equilibrium point. If the derivative at the equilibrium point is less than 0, then y0 is a sink. And if the derivative at the equilibrium point is equal to 0, actually you can't conclude anything from this test. There's no conclusion. This is the no conclusion case. You really would have to look at the graph. There are really lots of things that could happen. The graph could look like this at y0, and you'd have a node for the phase line, or it could look like this, and you'd have a node, or it could even look like one of these two. It could look like a cubic at y0, and in those cases, this one would give you a source if you drew the phase line. Having trouble spelling source, and this one would give you a sink. Just think about how the sign of the right-hand side changes to see that. So the linearization theorem gives you no conclusion, but you can still reach a conclusion if you draw the graph of the right-hand side f of y. All right, this linearization theorem maybe seems kind of insignificant in section 1.6 because we can always use technology to make these graphs. But we'll see when we get to chapter 5 that there's a higher dimensional analog of this linearization theorem that really is pretty fundamental, because it really gets tough to visualize what's going on when you go to higher dimensions. So we need a little practice with it here now. We'll see it coming to full benefit for us when we get to chapter 5. And so let me end now by talking a little bit about what this continuous differentiability means. You can certainly use that linearization theorem whenever you might need it. For example, in a purely qualitative problem, perhaps. Maybe you don't even have a graph, and all you've got are just a bit of information. Maybe you're just told you have a function f of y on the right-hand side, and you're told that the number 3 is an equilibrium point, and you're told that the derivative at 3 is positive, and that the function is continuously differentiable. Can you make some conclusions? Or maybe you're told some other things. Can you still draw the phase line? That would be a more abstract setting, even without a graph, where you could still perhaps be able to draw the phase line. And so you should make sure you think about problems like that. But what does this continuous differentiability mean? What I want to do is just show you an example of a function that's continuous, and in fact differentiable everywhere. It's got a derivative that exists everywhere, and that derivative is not continuous. So this function will not be continuously differentiable everywhere, at least. It will be everywhere except one point. Essentially, the function is this. I'm going to take x over 2 plus x squared times sine of 1 over x. Maybe you want to zoom in on that to make sure it's big enough to see that. As I type this function in, as it stands, it's actually not defined everywhere. It's undefined at x equals 0 if you think about it, because you have a 1 over x here. You can't divide by 0. Well, let's ignore that for the moment. Let's go ahead and enter that function and plot it. Let's try negative 3 to 3 first and see what it looks like. There we go. Something, if you focus in here, seems strange, seems to be happening perhaps near 0. Otherwise, it looks pretty ordinary. Let's go in closer to that. I'll try negative 1 to 1. You see that strange area expanding a bit. Now I think I'll try negative 0.2 to positive 0.2. Something strange definitely seems to be happening here. What in the world is going on? Well, maybe this is not too surprising. After all, sine is an oscillatory function. Maybe it was more surprising that it didn't seem to be oscillating much at first. Think about what's happening to sine of 1 over x as x goes towards 0. As x goes towards 0, 1 over x is getting really big, either positively or negatively. Let's imagine x is positive and going towards 0. 1 over x is getting to be a really big positive number. In fact, it's going to infinity as x goes towards 0 from the right. As the argument of the sine function continues to get bigger and bigger like that, the sine function has to oscillate. In fact, I guess infinitely often as we approach 0. Now, you can't literally see infinitely many oscillations here with the computer because it just doesn't have enough resolution at the scale that we have. But you see, it seems to indicate that perhaps these oscillations do continue and they're all sort of getting smaller and closer together. So it seems reasonable from this perspective that that perhaps could happen. And in fact, that does happen. There are infinitely many of these little bumps as you approach 0. In any interval containing 0, you get infinitely many of these little bumps. And the function does appear to be continuous at 0. We can't literally plug in 0 into the formula, but so technically there's a hole in the graph, but that's just a removable discontinuity. We can make the function continuous at 0 by defining it to be equal to 0 when x is 0. It's really a piecewise definition if we do that. That would work out fine. We could fill in the hole, and effectively we could think of this as a continuous function. And in fact, it's a differentiable function. The derivative, when x is non-zero at least, equals this. When x is non-zero, this is your derivative. What about the derivative at 0? Does that exist? Well, not by that formula. Will Mathematica do it this way? It says indeterminate. The derivative at 0 actually does exist. You'd have to go back to the limit definition of the derivative to see if you can find it. Let's see if Mathematica can do that. I'll just give it a try. I'm trying to find the derivative at 0. I'll type in f of h minus f of 0 divided by h. I'm letting h go towards 0, and I'm using this limit command and seeing if I get a limit. Well, it didn't do it. Okay, I have a little bit of egg on my face. Should have tried this ahead of time. But this function really does have a derivative at 0. Kind of looks like it should, doesn't it? Looks like perhaps the derivative, if you think about the slope here, should perhaps be 1/2. It looks like the line y equals 1/2, y equals 1/2 x there. In fact, the derivative does exist, but the derivative is not continuous. Watch what happens if we try to graph the derivative in this picture along with the function. This is pretty cool already. Ever seen that kind of picture before? Look at that derivative. That's the graph of the derivative. At least when x is non-zero, it oscillates infinitely often. Just like the blue one did, but this is a lot wilder. Oscillates infinitely often between, looks like about negative 0.5 and positive 1.5. It has no limit as x approaches 0. And even though I believe the derivative at 0 is defined, and I believe it probably is 1/2, this can't possibly be a continuous function at 0, because it has no limit as x approaches 0, this derivative. So the derivative exists everywhere, but it's not continuous everywhere. So the original function is not continuously differentiable. So what this highlights is that simple-minded approaches to abstract math can definitely get you into trouble. And if you think of the linearization theorem in too simple-minded of an approach, if you just think about the derivative being positive or negative, and what does that tell you? Without adding the extra hypothesis that the right-hand side function is continuously differentiable, technically speaking, you don't have a theorem anymore. The theorem needs to be true. You need to show that the conclusion definitely follows from the hypotheses, and that only happens if you assume that f of y is continuously differentiable. And that's the end of this video.